like we always do at this time. I go for mine, I get to shine. Now throw your hands up in the sky. I go for mine, I get to shine. Now throw your hands up in the sky.
Oh, it's that time of year. We are about to begin our ascent up the Mount Everest of calculus. We are going to begin our chapter on sequences and series. And ladies and gentlemen, it's about to get real here in a hurry in the next few days. From now until Christmas is going to be a real defining moment in our calculus experience this year, and really encourage over the next couple of weeks to really let it all hang out and to have no regrets and to take no shortcuts as we move along. Now, Mount Everest can certainly be beautiful, and from an observer's point of view, we can certainly appreciate the majesty of it. However, there are going to be some really intimidating days, some days where we're going to be halfway up that mountain here, as this picture suggests, and it's going to get quite blustery and overwhelming. But we're going to stick together. We'll take it one step at a time, and before we know it, hopefully we'll be at the peak looking down. Now, just like climbing any mountain, there's a strategic way about that, and we're gonna take the most strategic way we can to get to the peak of that mountain, the safest, most concise way. And I hope that you trust me along the way, and we'll get you to where you need to be. So, without further ado, let's go ahead and jump in. Well, being the beginning of the chapter, we want to be very thorough and detailed today and really hammer on some of our definitions so we develop a solid foundation for this monster chapter. First question right off the bat, what is a sequence? And I want to emphasize that a sequence is a list. That's probably our biggest buzzword today. It's a list of numbers that happen to be written in a specific order. So what we're suggesting here is that there's kind of a rhythm and a pattern. Well, that doesn't look like a C. There we go. In a specific order, there's a rhythm and there's a pattern, and it's not. It may appear chaotic at times, but there certainly is a pattern behind the list of numbers we're seeing. Now, the sequences that we're going to work with are called infinite sequences, and all that does is suggest that there is an infinite number of terms within our list. Okay, so we'll go ahead. We'll see a few examples of that before too long here. Another big key note here today is that a sequence is very, very similar to a function. Okay, the biggest defining element, though, is that the sequence has a domain such that we're only working with the set of positive integers. Okay, that's the domain, and we're going to say that n is my independent variable now. Traditionally, we're used to using x as our independent variable. Now we're going to use n, and basically all we're saying is when we say that this domain is a set of positive integers, n's allowed to equal 1, 2, 3, 4, and etc. Okay, n is not allowed to be a negative number such as -1 or -4 or 2, anything like that, and n is not allowed to be a decimal value like 1.5. Okay, it's only allowed to be positive integers in this pattern right here. Okay, just a few other notational ideas. We usually use these squiggly brackets a sub n. Okay, when you see this type of notation, we're talking about a list of numbers. In fact, those squiggly brackets right there do imply the word list. Usually if we expand it, we'd say it's a sub 1, which is the first term, a sub 2, comma a sub 3, comma dot dot dot, comma a sub n, comma dot dot dot, and close it with a squiggly bracket. A couple of key ideas there. We've got our first term, second term, third term. We've got our nth term, and we always finish with a little dot dot dot, signifying that yes, this list does continue. It never does end. We could always go a little further and a little further and a little further. Okay, we're going to practice listing the terms within a sequence, and the first one we want to tackle, we're going to define the sequence a sub n as 3 plus -1 to the nth power. Okay, and so we're just going to start off. We're going to try to, let's say we want to find the first 4 terms of the sequence. The first term is going to be 3 plus -1 to the first power, which 3 plus -1 is going to give you a 2. The second term is going to be defined as 3 plus whoops, I'm sorry, that's a negative 1 raised to the second power. That's going to make it a positive 1, so we end up with 4. And the third term, all I'm doing here is substituting a 3 in for n. So we've got our negative 1 to the third power, and that's going to give us a 2, and then we'll finish with a sub 4. That's 3 plus negative 1 to the fourth power, which leads us back to 4. So what we could do is we kind of summarize here that this sequence is 2 comma 4 comma 2 comma 4 comma dot dot dot, and that's, we would just simply, depending on how many terms I wanted, that's how we'd write it. Continuing in that same pattern, let's define another sequence named b sub n, and we'll define him. This one will get a little more exciting. We'll say it's n divided by 1 minus 2 times n. Okay, we'll do the same thing. We want to find the first 4 terms, and we can say that the first term, all I want to do is substitute a 1 in for those n's. Okay, and I got negative 1 for the first term. So we've got a lot of arithmetic and some mental math here today. The second term is going to be 2 divided by negative 3, so we could say negative 2/3. Let's see, the third term is going to be 3 all over 1 minus 2 times 3. That's going to be, let's go with 3 divided by negative 5, negative 3/5. And the fourth term, 4 all over 1 minus 2 times a 4. How about 4 divided by, we're throwing our negative, how about negative 7? So negative 4/7. Those look like our first 4 terms. So now we could just say the sequence looks like negative 1 comma negative 2/3 comma negative, whoa, I didn't realize I had 2 negatives up there, negative 3/5, negative 4/7, comma dot dot dot. Again, this simply is a list of numbers, and I want you to appreciate little things such as the use of these commas. That's going to turn out to be a big deal when we get to tomorrow and we start talking about a series, which, if I could emphasize one thing here today, a sequence and a series are not the same thing. Okay, one more example here. We'll define the sequence of c sub n, and it's defined as, let's see, n squared divided by 2 to the n minus 1, and same thing, we want to find the first 4 terms. Don't be afraid to hit the pause button here and see if you can get all 4 of these strictly on your own. You start to see how similar these are to, they're just like functions. We can plug numbers in. The only difference is the domain's restricted. Let's see, I got 4/3 for that one. C sub 3 looks like 3 squared all over 2 to the third minus 1. 9 over 7, I believe. Let's see, we'll create just a little more room. C sub 4 is going to be 4 squared all over 2 to the fourth minus 1. How about 16 all over 15? And we could then say that the sequence looks like 1 comma 4/3 comma 9/7 comma 16/15 comma dot dot dot. There is a special kind of a sequence called a recursively defined sequence, where what's going to happen is they're going to tell you right away what the first term is, and then what they'll do is then they'll give you some kind of a definition where each successive term is defined using the previous term. So we'll take a look at an example really quick. We're going to talk about the sequence called d sub n, and they're going to tell us ahead of time that the first term is 25. That's very kind of them. And then they're going to tell us that the n plus first term, and we want to, again, just a note on handwriting here, we're going to have very neat, meticulous handwriting. Let's make sure that subscripts stay subscripts and they don't accidentally migrate out of that subscript. So anyway, the n plus first term is defined as the nth term minus 5. So just as if we want to find the first 3 or 4 terms, we could say, well, when n is 1, we know that d sub 1 is 25. When n is 2, let me rewind just a little bit. Pretend I didn't say that. All right, so let's restart over. When n is 1, we're going to substitute a 1 in for all those n's, and that would give us d sub 2 is equal to d sub 1 minus 5. Now, you already know that d sub 1 was 25. So what that tells us is that the second term is really 20. Okay? Then moving on, when n is equal to 2, I'm going to substitute a 2 in for all these n's up here. That would mean that d sub 3 is defined as d sub 2 minus 5. However, you already know that d sub 2 is 20, so we ended up with a 15. Okay, Moving on, we'll pick, let's pick a new fresh color here perhaps. If I said n equals 3, I'm going to substitute a 3 in for all these n's up here. And we could say that d sub 4 is really defined as d sub 3, which is the previous term, minus 5, thus giving us 10 for that term. So the terms would go 25, comma 20, comma 15, comma 10, comma dot dot dot, and we've got our list of numbers. This just happened to be a recursively defined sequence. So hopefully that was a little warm-up we've gone through so far. Hopefully you weren't overwhelmed or intimidated by any of that yet. And I certainly don't mean to imply that tonight's lesson is going to be overly difficult, but I think throughout the chapter we are going to certainly be challenged. But let's get down to our chief concern here. Okay, let's jump right after here. What is our chief concern? What's the big thing we're looking for here? We want to know, do the terms within our sequence approach a limiting value? That's really what we want to know. Do those terms approach a limiting value? Okay. In other words, do we see, as let's say we wanted to calculate the first 100 terms within a sequence, it would be very tedious and time consuming, but what we'd want to do is, as we get out closer and closer to the 100th term and then the 1000th term and so forth, do those numbers within the list start to approach a certain specific finite number? For instance, a very nice example would be to look at the sequence 1 over 2 to the nth power. Okay, the first term is 1/2, and then 1/4, and then 1/8. The fourth term would be 1/16. The fifth term would be 1 over 32, and so on. And we're asking ourselves, okay, as we move from left to right and we get deeper and deeper into that sequence, what are we approaching? And hopefully you'd say to yourself that we are getting closer and closer to 0. And what we're going to later decide is, we're going to say, this sequence converges because it's approaching, okay, a finite number. We have a very special theorem regarding this, okay? To summarize this, we call it the limit of a sequence. And I'll tell you what, a power fight's going to become our best friend tonight, because basically we're interested in this. What happens as n approaches infinity, okay, when analyzing the sequence defined by a sub n? If the limit equals L, where L represents, let's just make a note here, L represents some finite number. Okay, if that limit equals L, then we're going to say, this sequence converges. Okay, however, if we find out that L doesn't exist, or maybe L equals infinity, or maybe L equals negative infinity, okay, then we're going to say that the sequence diverges, because in those three cases, L does not represent one specific finite number. What I want to do now is go back and look at some of the examples we did earlier today, already in our notebook. Remember that sequence a sub n that we defined as 3 plus negative 1 to the nth power? Okay. What we want to do is we want to ask ourselves, does this sequence converge or does it diverge? Okay. That's the big question. And remember the numbers we had within that list? We said 2, 4, 2, 4, da 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 da. Sometimes it helps to maybe visualize this pattern. Okay, and remember these are my n's and these are my a sub n values. So the first one we think of them as ordered pairs, 1, 2, and then 2, whoops, I didn't get that one high enough. Pretend that one's not there. 2, 4, 3, 2. 4, 4, and what you'll notice we do not connect these dots. We certainly do not connect them because the domain is only integers. But do you see a pattern, okay? If I continued to go further and further on this graph, would these dots be converging and moving in on one specific number? I would say no. This is an example where the limit does not exist, okay? In other words, can't make up its mind. It keeps oscillating from 2 to 4, 2 to 4, 2 to 4. We would say that this rascal diverges. The second example we worked with earlier, we defined as b sub n, and that was, we said, n divided by 1 minus 2 times n. And here's a great example. Let's go ahead and use that theorem we wrote down earlier, where we asked ourselves, what happens as n approaches infinity? for this particular sequence. And just go back to the good old days where we talked about power fights. We've got polynomial on top, polynomial on the bottom. In fact, to be more specific, it's a first degree polynomial on both top and bottom. If I compare the coefficients, I'm going to end up with -1/2. And since that's a finite concrete number, we're going to say that this sequence converges to a value of -1/2. And I think you could go back and look at that list of numbers. I think the list went -1 and then -2/3, and then -3/5, -4/7, etc., etc. And as we plotted those, I think you'd see that yes, the list does converge to a value of -1/2. The third example we worked with earlier, we defined as C sub n, and now the sequence said n squared all over 2 to the nth power minus a 1. Okay. Now, first of all, analytically, the limit as n approaches infinity of that sequence, what I do, I've got a second degree polynomial being divided by an exponential function in the form of 2 to the n. Okay. Basically, we could say that that -1 is quite irrelevant once n gets big enough. Now, this is an example of small over large when you compare the mathematical power of each of those functions. Therefore, the limit equals 0. If you wanted to analyze that one graphically, like I like to do, and you might have to refer back to earlier in your notebook to see what kind of values we got. I think when we plugged, let's see, I think we did the first 4 terms, and I think the biggest number we ever got was just a little bigger than 1. So we could say maybe here's 1 and here's 2. And on that list, we plugged a 1 in and we got 1, and then we plugged a 2 in and we got 4/3, so that's slightly up here. We plugged a 3 in and we got 9/7, just a little lower. We plugged the 4 in and we got 16/15. And what's happening here is, notice the sequence did start to climb early, but then it's starting, you'll see the pattern where it's starting to taper down. And what happens if we continued this graph further on, we'd notice that it does get the sequence does get closer and closer to 0. Now, in terms of the power fight, when you're trying to rank all these different mathematical functions and you're trying to decide, who's stronger, who's more mathematically powerful or dominant than other functions, we're going to find out that they generally follow this chain of command. We're going to learn shortly that the factorials are the fastest growing mathematical functions. They're kind of the Usain Bolt, so to speak, of math functions. Then exponentials slide in there in second place. Then we take a look at polynomials, where we'll compare the respective degrees of those polynomials. And then you'll finish with something like, usually logarithmics. They're kind of the turtles of the group. So anyway, I got our directions here are asking us to determine the convergence or the divergence of the sequence with the given nth term that I'm going to provide you here with shortly. And if it does converge, we're going to go ahead and find its limit, the value that it's converging to. So take a look at number 1 here. Our first example is the sequence defined as 3n squared minus 1 divided by 10n plus 5n squared. Okay, so our first goal here is to ask ourselves, what is the limit as n approaches infinity? Maybe just to save a little time here, I'll say that's really a sub n. So just the limit of a sub n. Looks like I got a second degree polynomial over a second degree polynomial dividing the coefficients. Again, the answer of 3/5. Therefore, we say yes, it does converge to a value of 3/5. It's as simple as that. Our second example, let's define b sub n this time as something new. Let's say e to the 2n power, we'll sneak the 2 in there, divided by n. Okay, we ask ourselves simply, what is the limit? What's happening as n approaches infinity? What if I was bored and I just decided for fun I wanted to list the first 1,000 terms of this sequence? How exciting would that be? What's happened is, we're asking ourselves, what are we getting closer and closer to as we go deeper and deeper into that list? Well, we have an exponential function divided by a very basic first degree polynomial. So I'm going to say that falls into the category of large over small. Therefore, the limit is infinity, and I'm going to make the conclusion that this sequence certainly diverges. They do not approach a specific finite value. Our third example is one that's going to be tough to analyze analytically, and I'll use a sub n again. And it says it's defined as -1 to the nth power divided by n. And we may find it helpful to analyze it graphically instead of analytically, and it's going to lead us to a new theorem by the time we're done with this example. But anyway, let's say I wanted to do it the long way, and I just wanted to list the first 4 or 5 terms to kind of get a feel for it. The first term would be -1, and then +1/2, and then -1/3, and then +1/4, and then -1/5. And then yada yada yada. Notice this is what we call an alternating sequence. Okay, what caused it to alternate? Well, you'll notice that little -1 to the end in the numerator, that's what's causing the signs to change each and every time. If we wanted to graph this rascal, the terms would look like this. Let's see, first, second, third, fourth, fifth, sixth term. There's -1, there's +1. So the first term was right here. Then the second term shot up here, and then here, and then here, and then -1/5 and -1/6. And you'll see what they're kind of doing. You see the pattern is they're starting to funnel from both above and below the x-axis, but they're starting to converge and funnel towards a height of 0 on both sides, okay? So graphically, I could say with extreme confidence that this particular sequence converges to a value of 0. Now, the reason I didn't really approach that one analytically is because of that -1 to the end in the numerator, and I said that this is going to lead us to a new theorem, and here's the new theorem that I want to throw in our notes here tonight. And that theorem says, okay, I don't have a real fancy name for this theorem, but basically the theorem says if the limit as n approaches infinity of the absolute value of a sub n equals 0, then we can say with extreme confidence that the limit as n approaches infinity of just regular a sub n also must approach 0. Now this theorem only works when we know that the limit equals 0. Okay, it does not work for any other finite numbers. This only works for when it's equal to 0, and I'll give you an example here. We'll tie it into the one we just talked about. The original problem said, let's see, we want to take the absolute value of -1 to the n over n. If we do take the absolute value of that rascal, we're going to simply get +1 over n, which is small over large and approaches 0. So that also implies, since the absolute value of that sequence converged, then the original itself must also converge. One last goofy one for this section. What if I had a sequence that I defined simply as -1 to the nth power, and that's it? Okay, again, just investigating the first couple of terms. The first term would be -1, the second term would be +1, and then -1, and the fourth term would be +1, and so forth and so forth. Now what's happening is it's similar to the example we did earlier where our sequence said 2, 4, 2, 4, 2, 4. What you see is we're not getting any closer to one specific value. And so what's happening here is it's oscillating strictly between -1 and 1. It can't make up its mind, and therefore we say it's considered a divergent sequence because the limit does not exist. Okay, we're going to talk about one of my favorite things in the entire course this year, and that's what it's called pattern recognition. And we're going to ask you to define the nth term of a particular sequence. Now, first of all, how would you even know that this is what we have here on the screen is a sequence without us actually telling you? Well, you'll notice it's simply a list of numbers, okay, where the commas kind of separate them, and you can identify who's the first, second, third, fourth, and so on term. When I try to investigate and identify a pattern, I just make a little note. There's my first term. There's my second term. Here's n equals 3, n equals 4. And believe it or not, something as simple and elementary as this technique right here will really help you kind of sort things out. We're looking for patterns, and when I looked at my numerator, it felt like it's an exponential pattern. Okay, it looks like to me that the numerator is always going to be equivalent to 2 to the nth power. Okay, you could pick any one of those terms and test my theory on that. For instance, if you look at that fifth term, 2 raised to the fifth power does give you 32 for a numerator. Now, when I started investigating my denominators, I didn't see that same exponential pattern. In fact, what kind of pattern do you see there? I think you'd agree that it's a linear pattern. And so there might be a little trial and error involved here. Might have to try a few different equations. But it looked like to me, if I double my n value and then subtract 1, I'll get the appropriate denominator. For instance, again, let's go to that fifth term. If I substituted a 5 in for my n down here, 2 times 5 is 10, minus 1 would, yes, give me that 9. And I could test the same theory on any of these other terms here to see if it does indeed produce that. But here is what I would consider a nth term for the given sequence. Boy, check this one out. I think you're going to have a barrel of fun with this one. I think this is an extreme upper echelon pattern. I think this one's just going to take us a lot of practice to get to a point where we can look at this one and recognize the pattern. There's a lot of key characteristics within this one. This is just a great example for us to challenge ourselves with. The first thing that I've seen students do in the past is they try to simplify the terms, and I'm going to really urge you to resist that temptation. They are doing us a favor by expressing them the way they did, okay? If I were to simplify each of these, I would be doing myself a disservice and making my job significantly more challenging. But anyway, I'm just going to identify them as n equals 1, n equals 2, n equals 3, n equals 4, and then finally n equals 5. The pattern is very challenging. The first thing I do want you to jump on the fact that this is an alternating sequence, okay? So what that means is I'm going to need a negative 1 to the nth power, okay, in there somewhere. Okay, and then I've got the fraction. My numerator is very challenging. I'm just going to cut to the chase on this one. It is exponential. It's in powers of 3, but what they did is they then subtracted 1. So that what they have here is it's 3 to the nth power, then minus 1. For instance, you could test that right here, for instance. We all know that 3 to the third power is 27, and then, of course, if we subtract the 1, we get 26, and so forth and so forth. We could test that on other terms. Right here, 3 to the fourth power is 81. Subtract the 1, you get 80. How about the denominator, though? This is an even more important pattern that we need to become comfortable with. Is it linear? No. Is it exponential? Perhaps it feels exponential. Rather, it's even faster than that. It's a factorial. The denominator is n factorial. For instance, 3 factorial is defined as 3 times 2 times 1, which is 6. 4 factorial is defined as 4 times 3 times 2 times 1, which would end up throwing you a 24. And then you probably guessed it, 5 factorial is equivalent to the 120. I want you to really get comfortable with this list of factorials and look for patterns that go 1, 2, 6, 24, and 120, etc., etc. That's going to be a real big one for us. But anyway, here's the final answer. That's how I would express the nth term of this given sequence. Speaking of factorials, I kind of want to finish the night off with just a brief discussion about factorials. You guys saw some factorials on your summer assignment, and you really did a fantastic job on that. That might have been our strongest portion of our summer assignment. But anyway, just to review, n factorial is defined as n times the next smallest integer times the next smallest integer, and we're going to continue that pattern until we hit 1. So just keep multiplying down. You know, for instance, 10 factorial would really be 10 times 9 times 8 times 7 times 6 times yada 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 until we hit 1. What if I said n plus 1 factorial? That would be, start with the number n plus 1, the next smaller number would be n, the next smaller number would be n minus 1, and then we would continue to multiply until we hit 1. 2 times n factorial versus the quantity 2n factorial, okay? In the first case, it's just 2 times n factorial, which is n times n minus 1 times n minus 2, etc., etc., okay? Whereas if I have parentheses around the quantity 2n, then it's, you start with the number 2n, the next smaller number, smallest integer would be 2n minus 1, and then 2n minus 2, and continue in that pattern until we hit 1. So it's going to be very important to feel comfortable working in terms of n. Let's see. We might as well go ahead and try to simplify one of these. Perhaps the directions, maybe an example tomorrow on our homework might say, take the expression n factorial over n plus 2 quantity factorial and just simplify it the best you can. What you'll notice here is I'm going to leave the numerator as is. I'm going to expand that denominator out a little bit, n plus 2 times n plus 1 times n factorial. And now what you could say is that this term cancels that term. We're simply left with 1 over n plus 2 times the quantity n plus 1. You're more than welcome to FOIL that out if you want, but not a requirement at all. So there it is, ladies and gentlemen. There's our first night on our climb to Mount Everest. We threw a lot of new things at you. A couple of key things that we're definitely going to have to review and continue to practice, especially that pattern recognition. I think that's going to be the most challenging thing, but we will get better at it the more we practice it. So rest up, and we'll see you tomorrow.